Welcome to the video of chapter number 4, Chemical Thermodynamics of Chemistry Standard 12th. In this video, we are going to study introduction and few concepts. Energy is broadly defined as capacity of a body to do work. In this chapter, we are going to study energy changes which are associated with almost all the physical and chemical processes. Now let us see what do you mean by thermodynamics. Thermo is derived from a Greek word thermos, which means hot or warm. Thermo is related to thermal energy. Thermal energy is in the form of heat. Dynamics is the science of change. So, we can define thermodynamics as the study of change of heat during physical and chemical processes. Thermodynamics has wide applications in various fields. To predict the feasibility of a given transformation, to derive the various energy changes taking place during a given change. Laws of thermodynamics are applicable in our day-to-day life. Engineers use these thermodynamics laws ranging from electrical components to nuclear power plants. Apart from our day-to-day life, it has wide uses. For example, in a power plant, burning of a coal is converted to electrical energy. This is transformation of one form of energy to electrical energy. In biological processes, internal energy is stored in the form of food. Energy is required in photosynthesis of plants. Hence, all these processes require principles of thermodynamics. We are going to study few properties of thermodynamics. System and its types, extensive property and intensive property, state function and path function, and thermodynamic equilibrium. Now, let us study what is system, surrounding, and universe. Consider a gas enclosed in a cylinder equipped with a movable piston. As shown in figure, if we study the change in volume of a gas, amount of energy released or gained by a gas when pressure is varied by putting a certain mass on the piston. In this case, the gas under the study is system. Thus, we can define a system is a part of universe under thermodynamic study. All other part of universe is surrounding. We need to remember that universe is made up of system plus surrounding. There are three types of system: open system, closed system, and isolated system. Let us first see open system. A system which can exchange matter as well as energy with the surrounding is called open system. For example, hot water in an open beaker. Here, water vapor and heat, that is energy, both are transferred to the surrounding. Any reaction carried out in an open test tube is an example of open system. Human body is also an open system. Photosynthesis carried out in plants is also an example of open system. Closed system. A system which can exchange only energy but not matter with the surrounding is called closed system. A hot water in a perfectly closed beaker. Here, water vapor cannot go out, but it can transfer heat, that is energy, through the wall of beaker. Any reaction carried out in sealed test tube is an example of closed system. Isolated system. A system which exchange neither matter nor energy with the surrounding is called isolated system. For example, hot water in thermos flask. Here, water vapor cannot go out or enter. At the same time, heat cannot go out or enter. Any reaction carried out in thermos flask is an example of isolated system. Coffee in a thermos flask is also an isolated system. A macroscopic system has certain thermodynamic properties such as temperature, pressure, volume, energy, density, etc. These macroscopic properties are classified into two types according to their dependence on the amount of substance or substances present in the system. Let us see first intensive property. The property which does not depend on the quantity of the matter present in the system is called intensive property. It is nature dependent. For example, boiling point, melting point, temperature, refractive index, density, specific heat capacity, molar heat capacity, optical activity, etc. Hence, intensive property is a property which does not depend on the size of the system but depends upon the nature and composition of matter in a system. Our next property is extensive property. Extensive property is a property which depends upon the quantity of the matter present in the system. It is quantity dependent. For example, mass, volume, area, work, energy, heat capacity, etc. Hence, extensive property is always depend upon the size of the system. Whenever an extensive property is quantified, it becomes intensive property. For example, volume. Volume is an extensive property, but volume per mole is an intensive property. Heat capacity. Heat capacity is extensive property, but specific heat capacity is an intensive property. Ratio of two extensive property is an intensive property. For example, ratio of mass and volume. Mass and volume both are extensive properties, but mass upon volume is equal to density. Here, density is an intensive property. There is another example, ratio of force and area. Force and area both are extensive property, but force upon area is pressure. Here, pressure is an intensive property. We have some key points with respect to these intensive and extensive property. Those are state of a system, state variable, state function, and path function. Every system can be described in terms of variables like pressure, volume, temperature, and energy. A known set of variables such as pressure, volume, temperature, and energy are associated with the system at any given instant, and this is called as state of a system at that instant. A change in even one or more of these variables changes the state of the system. For example, a system with the state A having the pressure P1, temperature T1 and the volume V1. Now, when the system reaches to the final state B, having the pressure P2, temperature T2 and volume V2. Pressure, volume, temperature, energy are thermodynamic functions. When we plot a graph with respect to the pressure and volume, the change in the pressure we can calculate by P2 minus P1 and change in the volume we can calculate by V2 minus V1. Hence, the system goes from initial state to the final state irrespective of the path followed. The changes in the pressure and volume are state functions which depend on only the final and initial state and are independent of the path followed. Hence, we can say that thermodynamic is a state function and not a path function. Whereas work and heat both are path function. Now, how do we say that work and heat are the path function? For example, a person may decide to hike up a 500 feet mountain. Regardless of what path the person takes, the starting place and the final place on the top of the mountain will remain constant. The person may decide to go up straight to the mountain or decide a spiral way to go to the mountain. There are many different ways to get the mountain, but the final and initial state remains the same. Now, how do we say that heat is a path function? Suppose a person wants to reach 4th floor from the 1st floor and he can take two ways, one through the ladder and another through the lift. In both the cases, initial and final state remains the same. But in both cases, the amount of heat he released is different. Hence, we can say that heat is also a path function. Now, what do you mean by thermodynamic equilibrium? A system is said to be in thermodynamic equilibrium when its state functions do not vary with the time. It means that when the state functions such as pressure, volume, and temperature remains the same and do not vary, then we can say that the system is at the equilibrium. The pathway or operation followed while going from one state to another state is called a process. The different types of processes that are common in the study of thermodynamics are isothermal process, isochoric process, isobaric process, adiabatic process, cyclic process, and reversible process. Now, let us see all these processes in the detail. Firstly, we have isothermal process. Consider a system containing an ideal gas enclosed in a cylinder fitted with a piston and is in thermal contact with the surrounding. Let T1, V1, T1 be the variables of the initial state, P2, V2, T2 be the variables of the final state. In this process, temperature of the system remains constant throughout the process. Hence, T1 will be equal to T2. Hence, we can say that the change in the temperature, that is the delta T, will be equal to 0. In this process, the expansion or the compression of the gas takes place when work is done at the cost of heat absorbed by the system from the surrounding and does not utilize or use its own internal energy. So, internal energy delta U of the system remains constant throughout the process. Next we have isobaric process. Let P1, V1, T1 be the variables of the initial state, P2, V2, T2 be the variables of the final state. In this process, pressure of the system remains constant throughout the process. Hence, P1 is equal to P2. So we can say that delta P, that is the change in the pressure, P2 minus P1 is equal to 0. Next we have isochoric process. Let P1, V1, T1 be the variables of the initial state, P2, V2, T2 be the variables of the final state. In this process, volume remains constant throughout the process. Hence, V1 is equal to V2. Thus, we can say that delta V is equal to 0. Next, we have adiabatic process. Let P1, V1, T1 be the variables of the initial state, P2, V2, T2 be the variables of the final state. In this process, there is no exchange of heat between the system and the surrounding. That is, we can say that Q is equal to 0. Consider expansion and compression of the gas. In this case, expansion of the gas takes place at the cost of heat absorbed from the surrounding, because exchange of heat decreases during the adiabatic expansion. Hence, temperature also decreases. During compression, the gas heat evolved which cannot be given to the surrounding since they are isolated. So, it is then added to the internal energy of the system. Thus, increases and hence temperature of the system also increases during adiabatic expansion. Hence, we can say that in this process, temperature and the internal energy is not equal to 0. We have two more processes, cyclic process and reversible process. Let's see first cyclic process. Now, it is a process in which a given state undergoes numerous changes and returns to its initial state is called as cyclic process. It means that in a process when the thermodynamic state undergoes numerous steps but still the variables remain same. For example, when the process starts from P1 V1 to P2 V2 T2, since it returns back to the final state and the initial and final states are same, hence we can say that change in the pressure delta P, change in the volume delta U, and the change in the internal energy delta U is equal to 0. Next we have reversible process. Now in the reversible process, driving and opposing forces differ from each other by infinitesimally small value. Consider a gas fitted with a frictionless piston. Now you could see in the figure that there are numerous weights kept on the piston. Let P external be the external pressure. Let P be the pressure of the gas. Now, if I am increasing the external pressure, that is, if P external is greater than the P, that is the pressure of the gas, then the gas compresses. And if P external is less than the pressure of the gas, then gas expands. Now, if I am removing the weights one by one, as you could see in the figure, as I am removing the weights, what is happening over there? The gas is expanding. But there is very infinitesimally change in the expansion of the gas. That is, there is infinitesimal change in the volume, that is dV. Hence, at each stage, When you expand the gas, there is an infinitesimal change and the equilibrium is attained at each stage. Hence, we can say that this process is such that there is equilibrium at each stage. We can obtain reversible process with the following conditions. When the driving and opposing force differ by infinitesimal small amount, the process is reversed by infinitesimal small change. It is a slow process and takes place in infinite steps. Every step, mechanical equilibrium is there with respect to the surrounding. Thank you so much for listening patiently.